Our moon, a familiar sight in the night sky, has captivated humans for millennia. Its soft glow has inspired countless myths and legends. However, the scientific story of the moon's birth is just as captivating as any myth. For centuries, scientists grappled with the mystery of the moon's origin. How did this celestial body, so large and so different from Earth, come to be our constant companion? Several theories emerged, each with its own set of strengths and weaknesses. Some proposed that the moon formed alongside Earth from the same primordial cloud of gas and dust. Others suggested that the moon was a wandering body captured by Earth's gravity. However, none of these theories could fully explain the unique characteristics of the Earth-Moon system. The answer, it turned out, lay in a cataclysmic event that unfolded billions of years ago. Imagine the early solar system, a chaotic and violent place. Planets were still forming, their orbits unstable, and collisions were commonplace. In this tumultuous environment, a Mars-sized object, which scientists have named Theia, found itself on a collision course with the proto-Earth. The impact was unimaginable, a cosmic clash of unimaginable proportions. Theia slammed into the young Earth at an oblique angle, delivering a glancing blow that sent shockwaves through both bodies. The energy released in this collision was staggering, instantly melting the surface of the Earth and vaporizing Theia entirely. Molten rock and vaporized metal were blasted into space, forming a massive, superheated disk around the Earth. Over time, this disk of debris, bound together by gravity, began to coalesce. Gradually, the particles clumped together, forming larger and larger bodies. Within a few million years, this process gave birth to our moon. This violent birth explains why the moon is tidally locked to Earth, always showing us the same face. The impact also tilted Earth's axis, creating the seasons we experience today. The giant impact hypothesis, while initially met with skepticism, has gained widespread acceptance due to a compelling body of evidence. One crucial piece of evidence lies in the composition of lunar rocks brought back by the Apollo missions. These rocks, when analyzed, revealed a striking similarity to the composition of Earth's mantle, the layer beneath the crust. This similarity suggests that the moon formed from material that originated from Earth's interior, consistent with the idea of a massive impact that excavated material from deep within our planet. Furthermore, the moon has a relatively small iron core compared to Earth. This supports the giant impact hypothesis, as the impact would have primarily ejected Earth's outer layers, which are poorer in iron. Another line of evidence comes from the moon's orbit and rotation. The moon's orbit is tilted relative to Earth's equator, which is unusual for a large moon. This tilt is best explained by a giant impact that knocked both Earth and the newly formed moon off their original axes. The giant impact hypothesis, though a dramatic scenario, provides the most comprehensive explanation for the observed characteristics of the Earth-Moon system. The giant impact hypothesis profoundly impacts our understanding of Earth's early history. The moon-forming impact was a defining event in Earth's evolution. It shaped Earth's atmosphere, oceans, and the emergence of life. The moon's formation stabilized Earth's rotation, aiding life development. The hypothesis also influences our understanding of planet formation. Giant impacts were common in the early solar system, shaping planets. The moon, though seemingly barren and unchanging, holds a wealth of information about Earth's early history. Because the moon has no atmosphere or plate tectonics, its surface has remained relatively unchanged for billions of years. This makes it a pristine record of the early solar system, preserving evidence of events that have long since vanished from Earth. By studying the moon, we are essentially looking back in time, gaining insights into the conditions that prevailed during Earth's formative years. The craters that pockmark the lunar surface, for example, are scars left by impacts from asteroids and comets. By analyzing these craters, scientists can estimate the frequency and intensity of impacts in the early solar system, providing clues about the environment in which Earth formed. The moon's composition also offers valuable clues about the early Earth. The giant impact hypothesis revolutionized our understanding of the moon's formation and Earth's early history. Many questions remain unanswered. What was Theia's precise composition? How did the impact affect life on Earth? Scientists continue to study the moon using various techniques. New missions aim to return samples from the lunar poles, revealing more about early Earth's water. Advanced simulations model the giant impact in detail, Studying the moon has implications for planetary science and human exploration. The moon offers a glimpse into the violent birth of our planet and our existence.